Good morning, good afternoon, or good evening, wherever you're at and whatever time you're watching this. Welcome to the MOOC class at IIT Madras. My name is David Trejo. I'm here to present on corrosion and service life of reinforced concrete structures. And really what I want to focus on is the influence of input variables. Yesterday I spoke about, or I shouldn't say yesterday, I guess my last lecture I spoke about the basics of corrosion. I talked about the physical system, I talked about thermodynamics, I talked about the kinetics of the system, and then I actually wrapped up with a little bit on service life. And I talked about the importance of service life and how it affects our society today, if we construct structures, and how if they're short-lived or they deteriorate quickly, that there's a significant problem with that. And so one of the things that I want to focus on today is I'm going to pick up on the service life. I'm going to reintroduce it briefly. I'm going to talk about the input variables that we need to predict the service life. And really one of my arguments is that we've done very good with modeling and the computational power that we have now to model and the service life. What we haven't done as well with is the input parameters, or the input variables that we need to predict that. And I'll talk about this, I'll talk about the influence, but I'll also talk about the need to standardize some of the testing. All right. Okay, so what I'm going to do is I'm going to give a brief review of service life of reinforced concrete structures. I'm going to talk about influencing variables, and I'm going to talk about 4 influencing variables. There's another one that is just a measure. It's a field measure. It's the concrete cover, and I won't address that. I'm going to talk about the chloride surface concentration. I'm going to talk about the critical chloride threshold. I'm going to talk a little bit about the Addmix chloride content. That's interesting because it seems like that's just a laboratory test that we should be able to do fairly easy, but there's quite a bit of controversy on that, and so I'll talk about some of those controversies and what we have to do. I'll talk about the apparent diffusion coefficient, and this is really just talking about a need. We haven't actually started addressing this. There's several tests out there, but those tests are not representative of field conditions, and so we need to make some changes to that. And then I'll go ahead and summarize. All right, so my objectives for the presentation is really to show that input variables for predicting the service life of reinforced concrete structures can significantly influence the prediction that we do. And I'll show some of these data. And the second thing is that significant research is needed in standardized testing to better assess these input variables. Those are the 2 big takeaways that I want to talk about today. All right. Let's go ahead and look at the brief review of service life. Let's try it again. All right, I showed this slide yesterday. How do we go about predicting service life, and what do we need to do, and why? Well, the reason that we need to predict the service life is because we spend a lot of money on these structures to construct them, to design and construct them, and we put them in aggressive environments. And these aggressive environments can be the ocean, it can be if there's freezing, it can be salt applications to the roadways, but we are putting our structures in much more severe environments. And so because of that, we need to look at the service life. I'll do a brief overview again of the why. What we do is we expose it to chlorides. Chlorides are transported into the structure and into the concrete, and it takes some duration to get there. And so what we do is we model the chlorides, the transport of chlorides into the concrete. And that's the key point, is how long does it take? And I did a little cartoon here, is we have chlorides on the surface of the concrete. You can see there to the right. I think it's going to show here to the right. Maybe not. Let's go back. Anyways, these ions in the electrolyte on the surface of the concrete, they are typically transported into the concrete, and I actually had a simulation there, but it just doesn't seem to be working. It's not important. Okay, so then what happens? How do we look at the service life? Well, the service life is really a function of the damage that the structure experiences. If we look at the damage as a function of time, what you can do is when you construct something, we have no damage, and then with time, it increasingly increases. And so you can see here there's some maximum allowable damage, and we call that the end of our service life. And so what's critical for us is when we're looking especially at chloride-induced corrosion is that at some point in the structure's life, corrosion starts, it initiates. And what we do is we want to determine that time from when we put it in service to when that corrosion initiates. There hasn't been a whole bunch on the propagation phase or the phase after it starts initiating, but there is some work starting now, and we should get a better handle on this. Right now, the time after corrosion initiates, we typically give it to 6 to 10 years, and then we take it out of service, or we do a major repair. So that's what service life is. And that time required to start the corrosion process is really what we're interested in here. I talked yesterday, or I'm sorry, I talked in my last lecture a little bit about the process. We talk about advection and diffusion and permeation and migration of chlorides. We have all these different mechanisms, but what we do is we simplify it, and we use an apparent diffusion coefficient. Using that, we actually solve for that. We come up with an equation for looking at the chloride transport and the time. And then what we do is we make some assumptions on the chloride concentration at the surface of the steel. And what we do is we come up with a time, and we call this the service life. That's that T right there is that time to corrosion initiation. Now there's four key variables that I wanted to talk about, and I'm going to show them to you here. Is that those are them? Those are the variables: the apparent diffusion coefficient, the critical chloride threshold, the Addmix chloride content (CI), and the surface chloride concentration. Those are the ones that I'm going to talk about today. Now, why? Why do we care about this? Well, it's important that, of course, if you have an equation and you have input variables, is that it's important that you understand how significant those can affect the output, and the output in this case being the time to corrosion or service life, or the major part of the service life. So let's go ahead and see how they influence. I didn't plot them all up here, but if we look at some of the variables, what you can do is, and this is just a sensitivity plot. What I did is I made an assumption on, I predicted the service life for one condition. And then what I did is I looked at, if I changed one variable at a time, how much would it change the output, or how much would it change the service life? And you can see here is that for the critical chloride threshold, this is the red line here, is that you can see that as I change that critical chloride threshold, so let's say I'm going from a conventional steel to maybe a corrosion resistant steel, is that I increase that, you can see that there's a significant improvement in my service life, or my time to corrosion. You can also see if I increase my cover depth, is that there's a cover depth being here, is that if I increase it, there's a significant increase. So really what we want to look at this is that the slope of the line is a critical part. The steeper the line, the more sensitive this equation is to that variable. And so I also show the apparent diffusion coefficient. As our apparent diffusion coefficient increases, is that the black line here is that our percent change in time to corrosion significantly decreases. So it's becoming much more, it's allowing the chlorides to be transported through the concrete much more easily. So you can see, I guess the point that I'm making here is that it's very sensitive to the input variables. And you can see here that if I increase the critical chloride threshold by a factor of 6, I actually increase the time to corrosion by a factor of 5. It's not linear, you can see there, but that's what we get out of this. So we're looking at the sensitivity of our variables. Let's keep going. You know, it's interesting to note that we think that we've been looking at service life for a long time, predicting service life. But if you look at the publications, number of service publications that are focused on service life, is that in the 1980s there was none. In the 1990s there was very, very few. In 2000, less than 20 years ago, is that there was only about 60 publications in service life. And so what I'm trying to show here is that although we seem to think that we've been doing service life for a long time, it's a relatively young time for this. And one of the first meetings on service life was in Washington, D.C. at the NIST, and they were looking at modeling the service life. And that happened in 1998. So we're looking at about 22 years, 25 years that we've been looking at this. And really the point is that we still have a long ways to go. And so it's okay to not know everything, and let's keep working on making it better. Okay, let's look at the surface chloride concentration. Now the surface chloride concentration, what happens is we expose the concrete to a chloride solution, chloride-based solution, whether it be the ocean or it be de-icing or anti-icing salts, is that there's chlorides build up on the surface. And that's one of the input parameters into the model, as you can see down here. There's SCS, is that, so that's important. And understand first, what do we assume now? And second is that how can we make it better? So what do we assume now? We assume that it's constant. We know it's not constant. In fact, a lot of the models assume it's constant, but there's actually a lot of the publications show that people have come up with different assumptions. One of the challenges with that is that we don't expose every concrete structure in the same way. And so we have to look at some variability. So all these different, several factors include the chloride exposure time, the chloride exposure conditions, the concrete constituent materials, the binding, all these different things, and those all influence the CS value. But many researchers have proposed other things, these are different models, and I guess you could see that some have said that it's constant, like I said earlier there, is that some have said that it increases linearly. We know that that's probably valid for a while, but it's not, surely after some time it's not that valid because that will go up to infinity. There's some that said that it asymptotically approaches some value. And then, of course, they do a bilinear. Those are all common models in the literature. But really, is that the right thing? And does it really represent field conditions? And does it really simulate the real physics of what's going on? And so, looked at some of the literature, and you can see the different models here. There's a wide range of models. But what is best, I guess, is the question. And so we can use all these different models, but if it doesn't represent the actual field performance, it's not realistic and it's not adding any value. Like I said, we've made significant advances in developing these models, but we've made very little advances in coming up with representative input parameters for these models. So you can see there's a wide range here. One of the things that I'm going to do is I'm going to talk about this function, Shikuri, developed recently. I think that it has some parameters that can be changed that are more representative of the field conditions, and I'll talk about that in a little bit. All right, let's keep going. If you look at the literature, is that you can see there's a wide range of assumptions and on these different surface chloride concentrations. You can see there's a wide range of distributions. You can see that there's a wide range of units. There's a wide range of mean values and coefficient of variation. There's different ways that they've assumed different ways that they've determined these values. Some of them they've assumed, some of them they've measured. But when you do this, it actually increases the variability of the model output. And so you can see there we have a wide range. Now, I'm not saying that those are incorrect. What I'm saying is that at the time, that's what they did. They're now in the literature, and if you go and use those values, you can actually get a wide range of output. And so what we did is made some assumptions on all the input parameters, just made them deterministic with the exception of one. What we did is we varied CS here. And if you look at this, what we did is we did time to corrosion here, and we look at the number of simulation, and the only thing that we varied was the surface concentration. And you can see that our model, it looks like there's some concentration of data between about 25 or maybe 20 and 40 years, but you can get anywhere from 5 to 300 years. And that's the point, is that if we don't have any standardized testing, we're going to get a wide range of service life, or time to corrosion values, which provide limited value from this great work that's been going on. And so we have to come up with a standardized test method. And so I said I was going to focus on the work by Shikuri, and it's here, the third one is here. But the nice thing about Shikuri is he lets you vary or change some variables. You can see there's different surface chloride concentrations, and from different authors. Don't know if they're all okay or right, but I'm going to show you, focus on the work by Shikuri. All right, one of the nice things about this, you can see the equation that he put up here to predict the surface chloride concentration. And it's a function of time, and it's a function of two other constants that he develops. And those constants are dependent on different things. So the particular one that we're looking at here is if we assume that A is 0.77 and we assume that C is 6, and we change B, what we can see is that the slope of this surface loading decreases. Now, why is that important? Well, it's important because, you know, if you're near a very high concentration, you're going to have a very high loading rate, and it's going to your surface concentration is going to increase at a fairly quick rate. However, let's say that you don't have a severe condition, and the buildup is a lot slower. Well, you can adjust this by adjusting this B value. He also, which I thought was another unique thing that he did, is that he changed, put a parameter in there where if there's a delay in exposing your structure to chlorides, is that you can actually account for this too. And so what he did is he put in a C value, and you can see that the larger the C value, the larger the delay in exposure. So when would this occur? Well, let's say that you had a reinforced concrete structure and you put an epoxy or surface epoxy coating on the surface. Eventually that wears off, the chloride starts getting into it, and you can see there that there's the increase in chloride surface concentration increases, but it increases at a later date. And so I think that was a very unique way of coming up with something that's realistic in the field. So that's some of the work that's been done on surface chloride concentration. He was validating some of this work, and that's going to come out soon, but I think this is an interesting and probably a model that is more representative of actual field conditions. All right, so I think there hasn't been a lot out there. There's been a lot of assumptions. They're doing some validation now, and I think that at some point soon we'll get to looking at what's the real surface chloride surface concentration, but we're not there yet. So let's look at the next variable, and the next variable is a critical chloride threshold. Now, I should say there's been quite a work going on in this area, but we haven't been real successful in coming up with what is a real value. And this topic I could talk for hours and hours and probably days and days on, so I'm going to have to be a little brief here because we are limited on time. But it's a very interesting topic, and one that's sorely needed. It's a significant variable. Remember earlier I showed if you change the critical chloride threshold of the steel by a factor of 6, you increase your service life by a factor of 5, or your time to corrosion by a factor of 5. So if we went from let's say a 1 kg per cubic meter a critical chloride threshold for conventional steel, and we went to a steel that had 6, which is not that high, 6 kilograms per cubic meter, we could increase our service life by a factor of 5 in that example earlier. Let's keep going. All right, let's look at the literature. The literature, Angst did a seminal paper on in 2009, and he looked at the critical chloride threshold values. And what he found is that the values of range from 0.04 to 8.3%. I mean, that's over 2 orders of magnitude. And so why are we getting this? What's happening with this stuff? It's one of the things that we've seen is that there's several issues. Surely how you test your chlorides, surely how you test the critical chloride threshold, and I'll talk about these now. One of the things that we look at is that what test do you use to test the chlorides? One could be the free chlorides, which they call, and I have free here in parentheses, or I'm sorry, in quotes intentionally, is because free could be water soluble, it could be pore extraction. It's really not real clear on a lot of this, what this was. And they talk about total, and we know that acid soluble testing is not total, but it's close to total. But you could see just the range just from the critical chloride, or just from the testing of the chlorides. So that's something that we need to think about. Should we be testing using the acid soluble test, or should we be doing a water soluble test? And if you're not familiar with those tests, it's just they're just different tests, and you can see that we're getting a wide range of values from the different tests. But I think one of the things that we need to do is we need to start standardizing the tests and not using both. And we'll talk about that a little bit later. Now, if we look at the chloride to hydroxide ratios, is that we have not only variability from the test method, chloride test method, but if we look at chloride to hydroxide ratio, now we have even more variability. And so what's right? You know, if we're looking at this critical chloride threshold, what's correct? And what best represents the actual field condition? We don't know. We need testing, but I'm going to show you some of the stuff that's in the literature. There's a wide range of stuff from the literature. You can see here that Shakuri and myself actually went and looked at it, and you can see that there's a wide range of distributions, different types of distributions. They use different units, and you can see here that some have used testing to predict this, but some have just assumed it. I think one of the challenges, I think we have to assume some things early on, but I think one of the challenges with that is that once it gets in the literature, it can continually be used. And if it's used to predict the service life when something has been assumed, we have to be very careful with that. So I guess the point is that there's a wide range of looking at this variable. There's been a wide range of assumptions, and we don't know how these apply to the actual conditions in the field. All right, if we look at the tests, and this is where I'm going to focus on a little bit here from here on out, is that there's a wide range of tests to actually estimate our critical chloride threshold. And you can see I listed 7 here that were in the literature. And so if we have a different test method, we're probably going to get different critical chloride threshold values. And Anks, when he did his work, he recommended that was a critical part. That was a critical thing in evaluating the critical chloride threshold. And so we can't have 7 tests if we want to actually get something that's representative of the field. You can see here that these test methods, looking at the different test methods, you can take, I summarized it in a table here. You know, what was the objective of the original test? Even though the original objective may have been different, it wasn't to get the critical chloride threshold, is that it's commonly used. All of these are commonly used to get that. And so what's measured and how do we measure and how do we determine what the critical chloride threshold? You can see that they use corrosion potential, macrocell. They use anodic polarization. They use OCP or macrocell current here again, linear polarization. They use a wide range of different tests, which will also influence the variability. What criteria do we use to say that now it's went from a passive state to an active state? You can see that there's some earlier work that had no criteria. It started cracking, maybe pulled it out. There's been some stuff when there's been a spike in current. I'm not sure that spike is the best technical term, but that's what they used. And then they have a wide range of things. But what's most important here is that you can see that some of these tests, 100 weeks. That's too long. We can get down to 1 to 9 weeks. There's a wide range of different test procedures and test times. If we want a test to be economical and be value adding to the industry, is that we have to develop a test that can be performed in a reasonable amount of time. If I'm introducing a new product to the market, a new reinforcing bar, I can't wait 5 years to have that evaluated. It's just not economically feasible. We have to do something in a reasonable time. So that's kind of the review of the different test methods. You know, the current test procedures vary significantly. They, to develop a realistic measure of CT and service life, we need to standardize the test, and that's my point here. So there's some, Angst made some recommendations on if we did develop a test, what we should do. There's been some additional publications, but I think this was interesting, is that he said that if you develop a test, it has to be ribbed and in as received condition. He also said that chloride has to be introduced via capillary suction or diffusion. He said end diffusion. I'm not sure we can do, I mean, we could do both, but I don't think we have to do both, or we could do one or the other. And that's important. The point he's making is that I think here is do not add mixed chlorides into your mix. And really, we have to use use electrochemical methods. Those are the three critical parts that he recommended. You know, we have to also realize that there should be some variability in this. The steel-concrete interface will vary. Surely they'll vary with the different tests, but just different steel products will vary a little bit. You know, different cementitious materials will vary a little bit, and so we should see some distribution in our values. But some distribution doesn't mean orders of magnitude distribution. I think we need to really have a standard test that can be representative of what's really in the field. And so what's important if we're going to develop a test? I think it needs to be repeatable. I think it needs to be simple. I think it needs to be economical. It needs to be timely, and it needs to be accurate. And I'm going to focus on this timely thing now because I think that's a critical factor. Of course, they all are, and we've looked at some of these, but timely is critical. So what we did is we developed a test procedure to predict or quantify the critical chloride threshold. And you can see here's our anode here. It's a relatively small sample, I don't know, 150 millimeters. And then we actually have that connected to our cathode here. And that, of course, what we want to do is we want to have some driving force. What we've done is we've raised the cathode above the anode. We have a solution here. We have it only up to the center of we have the bars horizontal, and we only have the solution in our cathode up to half the bar because we want oxygen to get into our cathode. And then we have those connected with both a salt bridge and a wire. You can see here is that here's our anode, a little bit more descriptive of it. And what we've done is we've intentionally designed it so we can have a dog bone. But this area in the middle, what we do is we expose this. Of course, as the chlorides are transported in, they'll get to the steel in this area first. And so once we get activation, we have some criteria for what is corrosion activation, we can easily break that off and do the testing. So it's fairly simple. I mean, this is one of the criteria, is make it simple. So what we would like to see from this test is we'd like to see if we have some test time, and this is not real data, this is just kind of simulated data. But we thought about, okay, before we actually develop this test, what do we want to see? Well, what we'd want to see is we would want to see some passive state at some time. And then at some point when the chlorides, there's sufficient quantities of chlorides at that interface, is we get an increase, a significant increase in whatever variable we're measuring, and we can clearly see whether there's an active state. And that was one of our objectives to do this, and we did. I'm not going to show the data. We have lots of data on this, and so it's very, very distinct where we can see that increase in what we're looking at is OCP, open circuit potential. Okay, so if we look at this region here, is that we crack this region off, we expose it for some time, and typically the test can be done in about 4 to 5 weeks. We cure, and then we actually expose it 4 to 5 weeks, no more than that. And you can see the region of mortar testing is here. It's from here to here. Easily breaks off the sample. That area right there, that's supposed to be our mortar. And you can see that we have this there. Now, what we do is we actually, when we measure this, we actually get some C-test. And this is this value here. We get an average value because we check out the whole cover. What we have to do is we have to correlate that with our critical chloride threshold, which is less than that. We've done that testing. I'm not going to show it now. It's very repeatable. I mean, it seems to run about 60 to 70% of the average value. So our C-crit is about 60 to 70% of our C-test. Okay, so we did a partial factorial design. You can see our variables. We changed our water cement ratio, our sand to cement ratio, our chloride exposure solution. We looked at different exposure cycles. It was continuously wet. We looked at 1 day wet, 1 day dry. We looked at 3 days wet and 4 days dry. And we wanted to see what would be most efficient, timely, and what gave the least variability. And then we actually, our exposure solution in our anode, because we have a small cover, what we did is we looked at different pH of our exposure solution. And that was 7 and 12.5. Okay, here's our full experimental program, and I don't think I want to get into all of this, but all those variables were assessed. Effective pH was done by comparing set number 2 and 3. Effective exposure type, we compared 3, 4, and 5. And then we separately could compare 13, 14, and 15. You can see effective water cement ratio. We compared 6 specimen set number 6 with set number 11 and set number 12. Effective sand to cement ratio. This is important because it affects the workability of the sand. The workability of the mortar. And the reproducibility of the measurements. We looked at set number 3, 10, and 11. And then, of course, the chloride exposure, we did 7, 8, and 9. and that was the concentration of the chloride exposure. Without getting into all that, we did a comprehensive study. We actually had about six different testing organizations evaluate this, and some round robin testing. And what we did is we came up with some value, some distribution. And what we did is this is some preliminary data. We're still getting, this is just from one lab, but it's very interesting that we have this range. We actually have done this was some of the preliminary stuff. We've done some more testing. We've tightened up the test, and this is even getting narrower right now. So what did we recommend? We recommended that the test be performed with a 0.42 water cement ratio, a sand to cement ratio of 1.375. An exposure solution of 2%. The pH of the exposure solution for the anode should be 12.5, and we recommended continuous exposure. And we did that for several reasons, because first of all, it's easier to handle. It's more economical. There's many places where testing is very expensive, and so what we did is we decided to do a continuous exposure. We think that we should have results from this fairly soon, but this is a standard test that we can use for assessing the critical chloride threshold, and this is important for reasonably predicting the service life, or time to corrosion and service life. It's a start. All right, let me summarize here. The literature contains a wide range of values for critical chloride threshold. It's using these critical threshold values result in a wide range of time to corrosions and service life. And it's almost provides no value. And so we need to standardize. Is that the lack of standardization is a result, and we need to standardize. I showed some preliminary results, and hopefully they'll keep going. Okay, so now let's look at what should be a very simple thing. We have chlorides in almost all of our constituent. Well, let me talk about that. Let's go ahead. One of the things that we have Portland cement, we have fine aggregates, we have SCMs, fly ash, slag, we have coarse aggregates, chemical admixtures, and we put water in our mix. And so typically all of those have some chlorides in it. Now, not all the time, but we can almost always find trace chlorides in our concrete. And so the question is if there's too much in there, we could actually initiate corrosion when we put the structure in service. Corrosion can start right away. Of course, we want to keep it below some threshold, not some threshold, I shouldn't say threshold, we want to keep it below some allowable content. These are all referred to as Addmix chlorides. The salt in these materials are referred to as Addmix chlorides, and that's very different from transporter chlorides. Addmix chlorides are with the constituent materials when the materials are mixed fresh, the fresh state. And so if we look at this, why do we care about this? Well, if you think about this, is that if we look at our initial cost and we look at the chloride limit, the allowable chloride limit here, is that if we actually let the allowable chloride limit go high, our construction costs will be lower because we don't have to transport any new materials in. Let's assume that you're by a beach, and let's assume that you have a great source of sand. Of course, it has very high chlorides, and just a word to the wise, don't do that. Don't use beach sand with chlorides in it. But let's say that you did, and let's say that it was allowable. You wouldn't have to transport more sand in. It would be much more economical, the construction cost. However, there's a cost for that. And that cost is the overall cost, because now if you exceed the level where the chlorides now initiate corrosion early on, of course you get corrosion, and you get you basically get a structure that won't last that long. And so we have to find some reasonable time, and you can see that's what results from if you actually have too much chlorides in your concrete when you mix it fresh. And so we have to find out what's some reasonable limit. What is it? I mean, there's a lot of specifications that say you can't have this much, but are they reasonable? I don't know. Well, I do have an opinion, but I'm not sure I know. But let's keep going. ACI is a leader in looking at these durability issues. But if you look at a lot of their stuff, is that there's a wide range of allowable chlorides. How much chloride should you allow in your concrete? Well, you can see here that it varies quite a bit. There was pre-1986. We thought with time we'd get a little better. We haven't got much better. You can see that there's still a significant variability in which document you use and how much chloride you can allow into your concrete. And it's also a little bit based on the exposure condition. So we have this current, and I guess the question is, which limit is correct? What should we? Should we follow the one on the left, or should we follow the one on the right? I don't know. And really, I guess the bigger question is, does it really matter? Does it matter? I think that I'll make a point here that it does matter. I'm also going to I'm showing you some data here in the U.S. We have 50 states. What we did is we went and looked at allowable chloride limits in those 50 state highway agencies, and you can see here that they have a wide range of variability. There's over 1,000 times difference on what they allow on the concrete. So if I'm in one state, I'm on the state lines between two states, this one, my concrete may be good, but if I step over this state line, it may not be any good because they have different allowable limits. And so the question is, again, is which is correct, and does it really matter? Well, I'm going to make a point here. It does matter. So these girders here were produced, and what they did is they changed the water source. And after several months, they realized that the water source had a high chloride concentration. So they did some testing, and what they did is they found out that one test was passing and one test was not passing. And so you think about, well, okay, no big deal, but the fact of the matter is if you don't pass this, these girders have to go and be thrown away. There's a significant investment. There's a significant cost. And this was in the millions of dollars and maybe tens of millions of dollars. And so you have to think about that. You have to think about, how do we measure this? And what's the right way to measure it? And not only how do we measure it, but what's the correct allowable limit? And so that we need to do some standardization in this also. We have to come up with what's a reasonable allowable limit, and really how do we test for it? Let's see. So it does matter. Let's look at if we change our Addmix chloride, our allowable Addmix chlorides, if we change that, and here we just varied it from 0.0 to 0.01% by weight of concrete. You can see that this particular one is down here in the equation, in our time to corrosion equation. And if we vary it, you can see it's pretty tight. It's ranging from about 55 to 80 years. But that's still a significant difference. And so, we didn't assume, we assumed 0 to 0.1% by weight of concrete. That's the range that we assumed. Of course, if we actually assumed different testing and different conditions, it could vary even more. But what this really assumes is that the chloride test result is representative of the chloride concentration over the life of the structure. Now, that assumes no unbinding, and the test procedures can be correlated. And I say the test procedures can be correlated, I'm talking about the acid-soluble test and the water-soluble test. So if we look at the one test, the water-soluble test is ASTM-C 1218. You can see that, and the acid-soluble is 1152. You can see in the acid-soluble test here, what we did is we actually looked at, 100, maybe 200, plus 200 samples, and we evaluated with a wide range of composition, and we evaluated the acid-soluble test, and it's a percent of total chlorides. And you can see that the acid-soluble test can typically go from 80 to 100%, but really it has a mean of 93%. Pretty good, almost the total chlorides, the mean is. If we, you can see the range there. If we look at the water-soluble test, the water-soluble test is that you can see here that there's a huge range. There's a significant range here. And so it goes from about, I think, 11 or 7% to up to about, 75% or somewhere. Now, one of the things that the standards assume is they assume that this water-soluble test is 75 to 80% of the acid-soluble test. Now you can see here, if you took these values here and you divided it by the acid-soluble test, that would range significantly, and that's not correct. Oops. ACI assumes that the ratio of the water to acid-soluble test is 75 to 80%. The results show that the ratio of the water to acid-soluble test is anything but that. It ranges from about 11 to 83% with a mean value of 45. So, and this is very dependent on the cementitious system. So the assumption is incorrect and it needs to be changed, and we're working on that now. Why does that happen? Well, it's really a function of binding. Is that if we look at ordinary Portland cement, if you look at as a function of the percent of Addmix chloride, as a function of bound chloride, you can see that the percentage decreases. So as the chloride content, or your Addmix chloride increases, that your binding decreases. And if you look at slag, you can see that there's a significant effect of the cementitious material type. And so we have to now consider these things when we're doing this. And the question is, you know, should we do water soluble or acid soluble to determine this? And there's been some more work that's been done, and it's seemed to be the case that maybe water soluble may be the most applicable. There's some cases where it's not conservative as it should be, but it's in the large majority of cases it is. So I guess the point is that the binding capacity is a critical parameter, and when we're assessing this. And really what we need to do is we need to come up with one standard test because it does affect the service life. So Addmix chlorides, there's no consensus on the amount of chlorides that can be introduced to the new concrete. There's no consensus on which test should be used to measure it. Chloride binding varies for the different cementitious systems, and these all will affect the time to corrosion and service life prediction. So although we're making some headway, there's still some mass confusion. And so we're working on it now. We're hoping to maybe standardize the testing for it and make some progress. All right, let's go into apparent diffusion coefficient, DA. So what we do now is we actually, to assess the apparent diffusion coefficient, is we get a sample, we cast a sample, and then we subject it into chlorides. Then we pull it out and we actually assess it using standardized tests for chlorides. It could be water soluble or acid soluble. The common field practice is to actually go out to the field, take a core, and then grind it in the lab and do the same thing. And we typically use potentiometric titration to determine the chloride concentration. Then what we do is to determine DA is we actually use a best fit curve. We grind it at different depths. We do the analysis. We look at the chloride concentration as a function of depth here, and then we can do a best fit curve, and we can get our apparent diffusion coefficient. And you can see that there is an influence of cementitious material type. Clearly, adding fly ash reduces your apparent diffusion coefficient. But if we go and we look at the literature on what should be the diffusion coefficient, there's a wide range of assumptions. You know, the distribution, the units, the mean, the coefficient of variation, whether it was assumed or was attested, or did somebody refer to somebody else. And again, I'm not being critical of this. What I'm saying is that we have to do this, but it's time now to start doing standardized testing to come up with hard data so we can predict this information. So the point is that there's a significant difference, and it can be a significant difference because, of course, some of the factors that we use to make our concrete changes, but right now with some of the predictions there's just too much variability. And so the values reported in the literature vary by several orders of magnitude. There's several distributions of coefficient of variation. In several cases, statistical distributions are assumed, and with very little justification. And so we have to be careful if we're using these in our service life prediction. And so the question is, how much can we use of these for actually doing service life of real structures? And again, not being critical, just saying we have to make sure we're careful between what we do in the lab and what we do in the field. So if we do it again, if we actually vary our apparent diffusion coefficient and we look at again, time to corrosion, we just simulate it. You can see here we just took values from the literature and we just make those assumptions. We assumed all the other variables to be deterministic. You can see here that our range is from less than 1 year to 300 years. Now, the point I'm trying to make here is that these input variables are significant, and they make a significant effect on your time to corrosion and your service life. So I guess the standard laboratory test methods are available, ASTM 1556, to determine the DA. However, this is not representative of what we see in the field structures. That is a diffusion, well, it's actually a advection and diffusion-based test, but that may not be what we're seeing in the field. So we have to be a little careful. And so I think what we need is some way to correlate our laboratory tests with our field structures, and that will make the test better. So I guess the point is that I'm going to summarize here is that we have to be careful. Is that there's a lot of stuff in the literature that can be used. You can put it into your service life prediction model. but it's probably not going to be representative of what you're going to see in the field. So actual service life or actual time to corrosion from what you see in the field and predicted corrosion, time to corrosion and service life could be very, very different. And so you have to be cautious with using your input variables. And I believe that we need to standardize these input variables. So let's look at the summary. We've made significant advances in predicting service life. Our computational power has increased dramatically. We have the models to predict the service life of reinforced concrete structures. However, the models for predicting the service life require input variables and on the exposure environment and the material characteristics. There has been limited standardization for assessing these input variables, and because of that, I think that we can see a wide variation in our predicted time to corrosion. And so, it's basically, right now we can get what we want, but it's not going to be representative of what we see in the field. And so I think that we need to standardize, and standardization is essential. That's what I have for today. Thank you for your time, and I guess you can't answer any questions, but if you did, you're always welcome to send them right to Thank you.